back to the Technical Guide for Startups, a video series where we help startups to start, build, and grow their businesses successfully and sustainably on Google Cloud. Hello everyone, I am Bhavika.
And I'm Anirudh, and we are both customer engineers at Google Cloud. In our previous video, we covered how to optimize for sustainability. Today, we will be talking about Cloud Spanner, Google Cloud's fully managed, horizontally scalable, and strongly consistent relational database.
Today we start off by discussing common challenges with traditional databases. Then we take a look at Cloud Spanner and how it helps to overcome those challenges. Next, we'll understand when Cloud Spanner is the right fit. After that, we talk about pricing model and how to migrate your existing databases to Cloud Spanner. Towards the end, we take a quick tour to Cloud Spanner console and wrap up with a customer success story. Let's start by identifying the challenges we face with traditional databases. Most databases have common characteristics which make them unsuitable for scaling elastically in cloud-native environment. Firstly, most DBs are only vertically scalable. You can add more CPU, memory, and disk to a database instance but cannot easily add more instances. This naturally requires downtime for scaling your database and imposes a practical limit. You cannot scale a single VM infinitely. When this limit is inevitably reached, companies normally resort to sharding, which means segregating the data on some criteria and storing each segment on a different database instance. While in theory, this enables horizontal scaling, but sharded databases are hard to manage and hard to keep consistent, leading to additional costs and operational efforts. Secondly, maintaining databases is traditionally a high-effort task, requiring a dedicated team of administrators to ensure business continuity. These teams need to handle hardware breakdowns, OS and software updates, and replacement of end-of-life resources, all while ensuring minimal disruption. Schema changes may incur downtime as well. Additionally, it is common practice to tweak database parameters, and administrators need to rebuild indices periodically to ensure optimal performance of these databases. Thirdly, keeping replicas in sync is a non-trivial task, and there will always be a finite replication delay in asynchronous replication. Lastly, it becomes increasingly difficult to have strong consistency across all replicas. Let's now talk about the cost of such systems. Most of it is hidden, as you can see this iceberg image. The top three issues are manageability, upgradability, and downtime. Let's say a database server can handle 10,000 players. Then you have to manage 100 servers for each million players, which makes it hard to manage. Next, when the players are from all over the world playing at any time of the day, the database has to function 24/7. In this case, it's impossible to find a maintenance window that suits everyone, making upgradability a major challenge in this case. And lastly, most traditional relational databases offer high availability using a failover mechanism. This means if the DB server fails, it will recover, but it generates downtime.
We've got you covered with Cloud Spanner, Google Cloud's fully managed, horizontally scalable, and globally consistent relational database. It provides industry-leading external consistency without compromising on scalability or availability. Cloud Spanner combines relational semantics with horizontal scale. You get relational semantics with schemas, enforced data types, strong consistency and ACID transactions across rows, and SQL queries using Google Standard SQL as well as the PostgreSQL dialect. And you get all this with horizontal scaling, so you can scale to large database sizes. This is all fully managed for you with either 4 nines or 5 nines of availability depending on whether you're running the regional or the multi-regional configuration. Cloud Spanner scales easily and quickly as an online operation with just a few clicks or an API call. And all of this comes with the familiar PostgreSQL interface. As we discussed previously, most traditional relational databases have limitations associated with replication, availability, and scalability. Non-relational or NoSQL databases address these limitations in many respects, but they have their own challenges, such as no support or partial support for SQL, eventual consistency at best, and limited data types and schemas, forcing significant re-architecting and placing limitations on analytic capabilities. However, with Cloud Spanner, you get full SQL support, including standard tables and columns that you'd see in any other relational database. Data is automatically sharded and resharded based on load and data size, and you get ACID transactions across partitions. In addition to all the traditional benefits of a SQL database, Cloud Spanner provides strongly consistent transactions, continuous availability, schema changes without downtime, fully automatic data replication, and server redundancy. But unlike many other relational databases, Cloud Spanner scales horizontally from one to thousands of servers. Let me illustrate with an example how Cloud Spanner helps overcome the challenges faced by a traditional database. Initially, we may start off by comparing a single instance of a traditional database on the cloud with a single instance of Cloud Spanner. As our application grows and handles more transactions, we naturally move to sharding to ensure performance and spin up more database instances. Spanner, on the other hand, allows us to easily horizontally scale out to achieve our desired performance, and you only pay for what you need. In fact, Google's internal Spanner instance has been handling millions of queries per second from many Google services for years, running various service backends such as AdWords and Gmail. Another important consideration as our application scales is ensuring that it is reliable and highly available. This requires creating yet more database instances in different regions and configuring them as replicas to create a fallback. We also need to ensure that the data in our primary instance is consistent with the replicas. With Cloud Spanner, all this is a one-click operation. Spanner manages replication and provides continuous availability while maintaining strong consistency across all the replicas, with no effort from the user. Next, let's consider security. Data needs to be encrypted at rest and often in transit as well to adhere to compliance requirements. This is quite challenging to set up manually and requires considerable development effort. However, Cloud Spanner provides both encryption at rest as well as in transit by default. Finally, when we consider the operational efforts of maintaining this database system that we have built for our application, a traditional database would need dedicated DBA teams for upgrading and patching the software and the underlying operating system, and running maintenance tasks to ensure optimal performance of the database. Since Cloud Spanner is a managed database, upgrades and maintenance of the database are automatic and cause no downtime to your application. Now, we can see the full picture of how Cloud Spanner enables us to simultaneously achieve scale, performance, and security, all while keeping operational efforts to a minimum.
Now that we have a fair understanding of what Cloud Spanner is, how do you know if Cloud Spanner is the right fit for you? Here are the 4 scenarios where Cloud Spanner becomes the most applicable. Firstly, if you have a workload that uses a NoSQL solution but needs transactional consistency without compromising on scale and availability, you can leverage Cloud Spanner's industry-leading external consistency. Secondly, if your workload requires you to shard your database for more read-write throughput or storage, you can move your data into a single Spanner database or instance to achieve the same results at low costs and low operational overhead without having to manage the complexities associated with sharding. Thirdly, if your data needs to reside in multiple regions and your application requires strong consistency and high availability, you can configure Cloud Spanner in a multi-region configuration to protect your database against regional failure. And lastly, if you store your business data in multiple database products with variable maintenance overheads and capabilities, then you can consolidate in a single spanner instance, resulting in significant cost savings and low operational overhead. If you were able to check one or many of these criteria, then Cloud Spanner is the right choice for your workload. In fact, you can get started with Cloud Spanner in production at as low as $40 per month by combining both granular instance sizing and CUDs. Now let's talk about how Cloud Spanner is priced. When you use Spanner, you are mainly charged for 4 components. Firstly, Spanner keeps track of the compute capacity, which is measured in processing units or nodes of an instance over time. You are charged for the number of nodes or increments of 100 processing units, which is 1/10 of a node. Spanner charges you for the average amount of data in your Spanner databases, including tables, secondary indexes, and metadata over a 1-month period. Spanner also charges you for the average amount of storage used by your Spanner backups over a 1-month period. And lastly, there are no bandwidth charges for Spanner replication or network ingress traffic. However, some types of network egress traffic are subject to bandwidth charges. Cloud Spanner also offers a trial instance to explore and become familiar with it, which is available at absolutely no cost for up to 90 days.
Okay, now you're convinced that Cloud Spanner is the right solution for you. But maybe your application uses a traditional database today. How do you start using Cloud Spanner to scale? Let's take a look at a simple, repeatable 6-step process to get started with Cloud Spanner. All migrations start with an assessment where we understand the environment, the goals, the risks, and the opportunities. Migvisor is a database migration assessment tool that analyzes database workloads and identifies challenges and optimization opportunities. This helps to automate the assessment process. We can now create a migration plan using the information from the assessment. Once the migration plan is in action, the first step is to modify the schema to be compatible with Spanner and optimize it according to best practices. We need to carefully convert data types and database objects from the source database engine to the destination. HarborBridge is an open source, self-hosted tool that is recommended for schema and data migrations for Cloud Spanner. Next, update your application to use Cloud Spanner. Google Cloud provides client libraries in many popular languages to connect to and interact with Cloud Spanner. You may also need to translate some queries in your application to Google Standard SQL, which is based on ANSI SQL. You can also opt to use our new Postgres interface, which allows you to write your queries in the Postgres dialect. The exact process of application migration will be unique to your use case. Then, migrate your data from the source database to Cloud Spanner. Again, HarborBridge is the recommended tool for low downtime data migrations to Spanner from supported source database systems. HarborBridge acts as an orchestration tool between Google Cloud's data services. It reads data using Cloud Data Stream, stores incremental changes in cloud storage, and writes data to Spanner using Cloud Dataflow. Once your data is migrated, validate that the data and the schema is consistent with the source database. It can be challenging to validate terabytes or petabytes of data manually, so you can automate this process with Data Validation Tool. It is a standardized data validation method built by Google and supported by the open source community that can integrate into existing Google Cloud products. It compares structured or semi-structured data from the source and the target tables and verifies that they match after the migration. Once you have validated your data and your application, you can cut over the production application to point to the newly migrated database. Voila! You are now ready to scale your application with ease using Cloud Spanner.
Let's take a quick tour to the console. Let's go ahead and create an instance and database in Google Cloud Spanner. As you can see that we are currently on Google Cloud Spanner page, let's go ahead and provision our first ever instance. Let's click on Create a Provisioned Instance, and you can see that the first thing that we need here is instance name. The name of the instance must be unique within your Google Cloud project. For the demo purposes, let's call this instance as test. The next thing that we need is instance ID to permanently identify your instance. The instance ID must also be unique within your Google Cloud project. You cannot change it later. The instance ID will be same as instance name unless you want to go ahead and change it. I am just keeping it the same. Next, we choose the configuration. An instance configuration defines the geographic placement and replication of databases in that instance. When you create an instance, you must configure it either as regional, that is, all the resources are contained within a single cloud region, or multi-region, that is, the resources span in more than one region. You make this choice by selecting an instance configuration which determines where your data is going to be stored for that instance. Let me go ahead and show you how multi-region configuration looks like. When I select multi-region, it allows you to choose multiple options where my instance can span across multiple regions in this case. However, for the demo purposes, I am going to create a regional instance only in US Central 1 region. You can see here that I also have an option to compare configurations. This allows to compare pricing and configuration between any of the two regions that you might want to. Lastly, you have to specify the amount of compute capacity for the instance. The compute capacity determines the amount of serving and storage resources that are available to databases in the instance. You specify the compute capacity by choosing processing units or nodes and then entering a quantity. When using processing units, enter quantities up to 1000 in multiples of hundreds, like 100, 200, 300, and so on, and enter greater quantities in multiples of thousands, like 1000, 2000, and so on. Each node equals to 1000 processing units. Cloud Spanner can handle millions of queries per second in low latency. Talking about storage, for instances smaller than one node, Spanner allocates 409.6 GB of data for every 100 processing units in the database. While for instance of one node and larger, Spanner allocates 4 TB of data for each node. For the demo, let's go ahead and input 3 nodes in this case, which means 3000 processing units, which in turn would allocate 12 TB of storage. Let's go ahead and now create this instance. As you can see, our instance is now created. Let's go ahead and create a database. Let me enter the database name. For the demo purposes, let's call this database as testDB. Now let's choose the dialect to use for this database. You can opt between Google Standard SQL and Postgres. For Google Standard SQL dialect databases, you can optionally provide a set of DDL statements that define your schema. Use the DDL templates to pre-fill common elements. If there are errors in the DDL, the Google Cloud Console returns an error when you try to create the database. Optionally, select a customer managed encryption key to use for this database. I'm just going to keep the default selections and create the database. Let's go ahead and click on Create option. As you can see that the database is now created. On the right pane, you can see the permissions associated with this particular database. Now let's go ahead and create a table inside this database. I am going to create a table singers by running the following DDL. Let's go ahead and submit this query. And you can see here the table singers has been successfully created. Now let's create an index for this table. Let's run create index DDL here and submit the query. In order to check the DDLs associated with this table, one can click on show DDLs here. As you can see in this case, here are the two DDLs that we ran. Let's go ahead and add some dummy data into the table singers. As you can see here, here's the schema associated with the table. As we go into data, there's an option to insert data. This in turn takes us to a query page. Here we can run the insert query. Now let me go ahead and run this query to insert dummy data into my table. As you can see that the query ran successfully, an entry has been added to my table singers in this case. Let's go ahead and add another row into our table singers. Executing this query, we see another row has been inserted successfully. Now that we have added some dummy data into our table singers, let's go ahead and display it. I'm going to be running a simple select star query in this case. Select star from singers. On executing this query, we can see that it displays the two rows that we had inserted earlier. That being said, you can also view this data from the data tab easily. With this, we have seen how easy and straightforward it is to create a Cloud Spanner instance. We created database, table, inserted data into it, and also queried it using SQL language. In the beginning of the video, we talked about Cloud Spanner being horizontally scalable database. Let's see how. Let us assume that you wish to scale in or out your application. For demo purposes, I am assuming that your application is not getting as much traffic as earlier, and you wish to scale into one node to save costs. As we can see in this case that your application is currently running on 3 nodes. Let's go ahead and edit this instance. We are going to change the number of nodes from 3 to 1. Let's go ahead and save this now. And voila! You can see that the compute capacity for Cloud Spanner has now changed to 1 node. This is how fast and seamlessly Cloud Spanner can scale horizontally. And with that, we have learned how to work with Cloud Spanner.
Let's now take a look at a real-world example of how Cloud Spanner is helping companies scale their business. ShareChat is an India-based social network company which serves over 160 million monthly active users who share and view videos, images, GIFs, songs, and more in 15 different Indian languages. With demand rising for local language content and an increase in online interactions in response to the COVID-19 crisis, ShareChat needed a more efficient way to scale dynamically and allocate resources as needed. When traffic unexpectedly grew by 500% over just a few days, ShareChat were able to horizontally scale with 0 lines of code change by migrating to Cloud Spanner. Moving over 120 tables with 17 indices also helped them to reduce their costs by 30%. Cloud Spanner helps ShareChat achieve strong consistency across multiple locations without having to rethink their existing data systems.
And with that, we have come to the end of today's video. All in all, we have covered an overview of Google Cloud's Cloud Spanner and how it helps resolve the challenges with traditional databases. We dived into to identify when Cloud Spanner is the right fit for you, its pricing model, and how to migrate to Cloud Spanner. Lastly, we saw a demo and wrapped it with a customer case study. For all those of you who are keen to learn more about Cloud Spanner, please refer to the links in the description box to get additional resources.
Coming up in our next session, we'll be covering AlloyDB. We'll start off with an introduction, discuss the advantages of AlloyDB, and dive into its technical details. Finally, we'll see AlloyDB in action with a demo and a customer story.
And that's a wrap. Don't forget to like and subscribe to our YouTube channel and click on the bell icon to get notified each time a new video is posted. Thank you and stay tuned for our next video.